Hello, welcome to the second video from chapter 17. In this video we'll go over standing sound waves and then beats. So we're going to skip a lot of sections on interference for sound waves and just go to one interesting effect for sound waves called beats. It relies on interference, but we're not going to do a lot of the math, so we're just going to look at the main effect. The problem that we want to be able to solve is given the fact. So given a closed open pipe, so imagine that you have a pipe made of metal and it's just a solid wall on this side, but it's open to the atmosphere on the other side right here. There are certain frequencies, certain wavelengths of waves that will set up standing sound waves. So we need to talk in this video a little bit more about what that means. It's not as obvious for sound as it is for waves on strings. But there are waves on strings, there's a fundamental, and then we want to know what the frequency of the next harmonic is. So there are special frequencies that the pipe will resonate at. There are certain frequencies that the pipe can effectively transmit sound at. And the fundamental is the one where it transmits the most sound at. But there are also overtones, and so we'll talk a little bit more about that. Okay, so I want to really focus on this closed open pipe. So the way that we've been talking about standing waves from the last video is that there are nodes and antinodes. So if I were to just guess what the standing wave is that could fit in here, so maybe there's a node on the left-hand side and an antinode on the right-hand side, right? It looks like there's something clamped down on the left-hand side and nothing clamped on the right-hand side. So I might guess that the biggest frequency that I could fit in there would look something like this. And I would be right, but we have to really break down what this means, what this graph means. So to give an idea of what's going on here, I want to focus on what sound is. And sound is a longitudinal wave where the particles are oscillating in the direction of propagation. So here we're focusing on sound waves that are moving left-right. So we're going to look at left-right displacements of particles from equilibrium. This particle, a sound wave particle over here, is free to move left-right as much as it wants, right? So a standing sound wave that's set up here, this one has an amplitude that is maximal. So this black line is showing. Remember what the standing waves represented in the last video. The standing wave, we're drawing the amplitude that's showing the maximum amplitude of a particle at that position. The particle over here will have, so the dot is representing its equilibrium position, but really the particle right there is oscillating back and forth. But with an amplitude that depends on where it is in the pipe. And now it's making more sense why this spot right here would be a node. So we call this a displacement node. Displacement node. So in terms of displacement, a particle there can't move, cannot oscillate, and so it has to be a node right there, whereas it's free to oscillate on this side. So that gives an idea of what the node means. There's a displacement node, and over here, on any open end of a pipe, you have a displacement antinode. Okay, your book, though, also talks about the fact that we don't have to describe sound waves in terms of displacements. So one way of talking about sound waves, so for sound you can talk about it two different ways. So sound you could talk about delta x as a function of x and t. So this could be a sinusoidal function, so a cosine or sine, a bunch of stuff. So you can talk about it in terms of displacements, or you could talk about it in terms of pressures. So you could talk about sound waves either way, but these two ways of talking about it are out of phase from each other. So displacement is literally just thinking about where the particle is and how much it can oscillate around. Pressure, though, is going to be pretty different. And in terms of pressure, the open end of the pipe is exposed to atmospheric pressure. So here the pressure has to equal, pressure must equal atmospheric pressure for any open end. So a displacement antinode is also known as a pressure node. Right? The delta P has to equal 0 because we have to have pressure equal to atmospheric pressure. Whereas a closed end of the pipe, this can be a pressure antinode. We can have pressure buildup, or we could have pressure less than atmospheric pressure near the wall of the pipe right here is not open to atmospheric pressure. So it's important to know that when for throughout this video, when I draw standing waves in the pipe, I'm going to be drawing the standing wave, but showing the displacements. So in this video, we're going to focus on displacement nodes and antinodes. If I were to draw pressure nodes and antinodes, the closed end of the pipe would be an antinode, and then I would put a node right here. So just the fact that I'm drawing a black line right there with the antinode right here means I'm focusing on the displacement nodes and antinodes. Okay, so continuing on with the closed open pipe. So we're told, so let's look at this problem. We're told that the fundamental frequency is 300 hertz. So what that means is the fundamental is the lowest frequency. Fundamental frequency. This is the lowest frequency. And remember, lowest frequency corresponds to largest wavelength, so longest wavelength that fits, quote unquote. Lowest frequency standing wave that, quote unquote, fits. So what I drew right here, so in black for this closed open pipe, is I drew a quarter of one whole wavelength of a standing wave. And that is the longest wavelength that fits in that pipe. Longest wavelength is smallest frequency. So this graph right here is showing the fundamental frequency. And this is the one that it's easiest to resonate. So if we just knocked on this pipe, if someone just hit it with a mallet, it's going to produce sound waves that emit from this pipe. And the majority of that energy is in the fundamental frequency. So that's why we're focusing on this so much. So as long as you know the length of the pipe and the speed of sound waves, you can determine the wavelength and the frequency of these waves. Okay, so let's focus on this one. So this problem. Okay, so for a closed open pipe, the fundamental is going to look like this for the displacement nodes and antinodes. So that's what the standing wave looks like. This is the fundamental. The next one that we can fit in there, so the rules when you're drawing these things is that any walls, any closed end of the pipe has to be a node, and any open end is an antinode. So I'm going to start just going up. That's the convention, but it really doesn't matter because remember this thing is bouncing up and down. So we need to come back down, and then have an antinode right there. So this is the first overtone, or the so first overtone, the second harmonic. So fundamental or first harmonic. Maybe I should do that in black pen. Fundamental or first harmonic. So this one, for closed open, it's a little. So notice how I'm avoiding. Your book gives specific formulas for this, and for an open closed tube, see how they label the M values with just odd numbers. So I'm going to avoid these formulas as much as possible. I think it makes a lot more sense, and it makes problems a lot easier if you just draw the standing waves that can fit in the pipe. We're not going to be dealing with questions that deal with the 17th harmonic in general, or things like that. So in general, it's just the easiest to draw these things. So what I drew right here is the second allowed frequency for standing waves. So your book would call this m equals 3. But really, it doesn't matter that you know the m value unless you're going to plug it into that formula. All right, so we're gonna answer this question without using the formula. And if you want, you can compare it to the formula later. But I want you to be able to solve these without relying on the formula. Okay, so now let's compare these two. So I guess just to be consistent, I'm going to call this well, I'll call this fundamental and then next. So fundamental and next. So because of the ambiguity with second allowed is m equals 3, I'm just going to call it the next one. So lambda for the fundamental is, now I'm just going to introduce a length of the pipe, L, right here. So I just want to relate lambda to L, because I can do that in both cases. So lambda for the fundamental, it looks like if I take the length of the pipe, looks like that's lambda over 4. I would need to extend the length of the pipe by 4 in order for, see this fundamental, in order for it to come back down here. That would be 2L, and then 3L, and then 4L. So for one whole lambda, that's equal to 4 times the length of the pipe. Now lambda for the next higher frequency. So I want to count, it's easy to see in these graphs where the quarter cycles are. So see how whenever you go from a node to the next antinode, that's a quarter of a wavelength. So that's 1/4 wavelength, that's another quarter of a wavelength, that's another quarter of a wavelength. So for me, the easiest way of finding out what lambda next is I could say, well, it's 3/4 times whatever that wavelength is, lambda the next higher frequency, is equal to the length of the pipe. So I'm just tracking it. It took 3 of these quarter wavelengths to get to the length of the pipe, which means that lambda next is 4L over 3. So if you look at this equation for open-closed tube, you can kind of see how these agree. So see that lambda m is 4L over m. So if I plug in m equals 1 and m equals 3, I can get those two facts for the two different lambdas. But it really wasn't hard just to draw them, right? And you might have to draw it anyway. I mean, a problem might explicitly ask you to draw the standing waves. So you need to know how to do this anyway. Okay, so what is this saying? The next allowed frequency is 1/3 the wavelength. So 1/3 the wavelength means 3 times the frequency. Okay, so the next, so continuing this on, so F next is 3 times F fundamental. And the reason for that is that V didn't change. The speed of the wave didn't change. Remember, the speed of sound waves is 343 meters per second. If we're changing what harmonic we're looking at, we're changing the frequency of the harmonic, changing the frequency of the wave, changing the lambda of the wave, which changes the frequency. It doesn't change the speed of the wave. So finally, we're able to answer our question. If the fundamental is 300 hertz, what's the frequency of the next harmonic? Looks like it's 900. So 3 times 300 hertz would be 900 hertz. So I mentioned that if you struck this pipe, you would mainly hear the fundamental, but you also hear these overtones. You also hear the other standing waves that are allowed. There's just less and less energy in each of the subsequent harmonics. So you'd hear mainly 300 hertz, but you'd hear a little bit of the 900 hertz as well. So you could imagine doing these kinds of graphs or drawing these sort of standing waves for open pipes as well. I think it's pretty clear, and this graph is summing up, the first few harmonics for the 3 different combinations. So if you look at figure 17.15 on the left here, and you look at C, open closed, and just focusing on the blue one, those are the displacement nodes and antinodes. You can see exactly what's going on, and those are, so notice it's the open close that restricts to m equals an odd number. And the only reason, the main reason they do that is to just have a nice equation that they can write down, where it's the same equation. They don't have to split up odd and even m. But yeah, like I said, you want to be able to draw these things rather than just rely on these equations. All the students I've seen who just try and plug in these equations, they tend to not do as well in the exam as people who can just draw these things. Yeah, so your book goes into a little bit more information about musical instruments and how this relates to them. But let's go ahead and skip over onto beats, all the way to 17.18 beats. So there's a lot of math here, and it can be difficult to see what the point of all of this is. So let me just emphasize what beats are all about. So when you have two waves of approximately the same frequency, of almost the same frequency, but not quite the same. So it's F1 and F2 that's about equal to F1, but not exactly equal to it. Then what you notice is you really hear or see, depending on what kind of wave you have, you really hear the difference in those two frequencies. Then a beat frequency F2 minus F1, and it doesn't matter which one's bigger. So that's why, you know, if F2 is bigger, it's F2 minus F1. If F1 is bigger, it's F1 minus F2. So just to handle both cases, we just put an absolute value. Then a beat frequency is observed or heard. Observed or heard, depending on whether you're talking about what kind of wave you're talking about. So there are lots of different examples of this. This book one is pretty nice. So here we just have a graphical representation of beats. So here, 27 lines per inch. So you have to imagine that this thing is 2 inches. So I don't know how big your computer screen is, but it's about 2 inches across from the very left of this to the very right of all these lines. 27 lines per inch and 25 lines per inch. And you can really notice the what stands out here is that, so see, your book labels this the visual beat frequency is 2 per inch. So the two waves on top of each other will line up for constructive interference. Looks like, see at the center right here, and at the center right here, see where the two lines line up. They mismatch exactly halfway in between. So in terms of sound, what happens is if you have two musical notes that are almost at the same frequency but not quite, you hear sort of a wow, 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 wow. And the frequency of that, how many times do you hear so what I'm doing, wow, 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 wow. I'm doing it at about 2 or 3 hertz. 2 or 3 times per second do you hear the wow, wow. And so what that means is that you hear that when you have two notes that are at frequencies that are off by about 2 hertz, 2 or 3 hertz. This is useful if you're like tuning a musical instrument, for example. If you have something that you know is at perfect pitch, and then you have something else that's maybe slightly too low, you just play both together, and it will help you tune. Another, I mean, this comes up all the time. It's so I don't know. So sometimes you ever like are in a daze in the car and you see windshield wipers that they start off. So there's 2 of them. Sometimes they start off in phase with each other, and then they keep going back and forth. And if they're going slightly different frequencies, you know, a little bit different, then they start to mismatch, right? So say this goes back and forth 1.00 hertz, 1.00 times per second, and this one is going a little bit faster. The one on the right is 1.02 hertz. Right, so it takes just a little bit less than a second to go back and forth. Then what you see is that they line up, and then they mismatch, and then they realign. And the amount of time that takes is, well, I can subtract these two and take the absolute value. And it looks like that's 0.02 hertz. Or in other words, it would take 50 seconds for them to line back up again. So So, if you're really bored on a car ride and you just stare at them for 50 seconds, you can see it very gradually become out of phase with each other and then in phase with each other. So that was windshield wipers. Another place you see this is like ocean waves. So if you're a surfer, then sometimes you have small waves and sometimes you have big sets that come in. And really it's because you have swells that have almost the same period, in other words, almost the same frequency, but not quite. So sometimes these swells constructively interfere with each other to make big waves, and sometimes they destructively interfere to make smaller waves. So surfers are used to this too. The problems, luckily for you, the problems that have to do with beats tend to be really easy. So looking at the stop to think on the left, you hear 3 beats per second when 2 sound tones are generated. The frequency of one is 610 hertz. The frequency of the other is, well, it has to be off by 3 hertz, 3 beats per second. So it's either 607 or 613. So it looks like the answer would be F, either B or C. Yeah, that's it.